In this video, we're going to take a look at doubling time and half-life using the rule of 70. So these calculations will be approximations. To start off with our objectives, in this video, you will learn what doubling time and half-life are, how to approximate both things using the rule of 70, and how to calculate values based on either an initial value or a final value. So we're going to learn how to use those half-life and doubling times to perform calculations. Again, I want to stress that we are going to be approximating using this rule of 70. There are ways that we can calculate exact values for exponential growth. That is not what this video is going to do. So let's start with a couple of definitions. The doubling time is the amount of time it takes for an amount of a substance to double in its initial value. I've left that word amount very, very vague for a reason, because that amount could refer to anything. It could be some sort of substance, some sort of molecule or atom. It could be a population, a number of animals. It could be any number of things. Anything that we're trying to measure that grows exponentially or shrinks exponentially, decays, that will have a doubling time or a half-life. Doubling time, how long it takes for it to double. The half-life, exact same idea. It's the time it takes for an amount to become half of its initial value. I think these are incredibly simple definitions, especially as doubling time has time right in it, right? It's the time needed to double. Half-life, we do have to remember that half-life is also a time. It is the time it takes to half. To find these, we have these two formulas, and these are the approximations. These are approximations for doubling times and half-lives. They are a nice, simple little formula. What it tells me is that I can find my doubling time, T double standing for doubling time, by simply taking 70 and dividing it by the percentage, P standing for the percentage of growth. Half-life, we can take 70 and divide it by the P, which again, that P is standing for, I'll write it down here, P is the percent of growth or decay. So they work the exact same way. With doubling time, something is growing. With half-life, something is decreasing. But again, we don't even have to change that percentage to decimal form. We just leave it exactly as it is. Makes the calculation super, super simple. We're going to take a couple examples. Let's start with example 1. The growth rate of bacteria in a refrigerator is 5% per day. Estimate the doubling time using the rule of 70. Right, so we're asked to estimate the doubling time using my above formula. I'm taking 70 and dividing it by the percentage, not converting it, just leaving it as the 5. And 70 divided by 5 is 14. Now we do want to make sure we always include units. So because that percentage was per day, that means our unit here, time, days. So doubling time, the amount of time it takes for our bacteria to double, 14 days. So if you started time 1 with 1 bacteria, 14 days later you'd have 2. 14 days after that you'd have 4. 14 days after that you'd have 8. Every 14 days that number is going to double. Let's look at example 2. Carbon-14 breaks down at a rate of 0.0122% per year. Estimate the half-life using the rule of 70. It's going to work the exact same way. We're going to call it T half because now this population is decreasing. It's breaking down or getting smaller by a rate of 0.0122%. So I'm going to take 70, I'm going to divide it by the 0.0122. It is already a percent, so I'm not going to convert it. I'm not going to change it. I'm just going to leave it in that form. And I get 5,737.7. I'm going to round this. It is 5,738. When we round to the nearest whole year, that's an approximation. It's not an exact number. And once again, we need to make sure we include units. So we had per year. So this would be years. Every 5,738 years, an amount of carbon will break down to exactly half of what it was. This idea is used in carbon dating. Let's take a look at a third example. Population of 30 deer are displaced by a new housing development. They travel to a new forest without any deer. Deer multiply at a rate of 3.5% per year. How long until there are 6 deer, 120 deer? So I'm asked to do a little bit more in this one. I'm not just strictly figuring out doubling time and half-life. We are dealing with a doubling time because we have a increasing rate. Doubling time always going to be with that increasing. Half-life is a decrease. So we do have a doubling time involved. And notice the amounts we have. We started with 30, we want to know 60, we want to know 120. Well, 60 is double 30, 120 is double 60. And so what we need to do is we need to figure out the doubling time, because that number of years will give me how long it will take to get to 60 and then to 120. So let's do that calculation. T double is going to be equal to 70 divided by my percent, 3.5. And we get 20. And because we had per year, this will be 20 years. It takes 20 years to double the population. So what that tells us, 60 deer will be present after 20 years. We started with 30, so if we double 30, we get 60. So one doubling period, one increment of doubling time, 20 years, will get me to double the number of deer, or 60 deer. 120 deer will occur. Clean that up a little bit. An additional 20 years, or 40 years, after the deer first moved in. We had two doubling periods. We doubled from 30 to 60, and then we doubled again from 60 to 120. So it makes sense. We've doubled twice. That's 20 years and 20 years, or 40 years. Now this was a relatively simple problem to figure out because we had that exact amount of doubling, 30 deer to 60 deer, 30 deer to 120 deer. But it would really be nice to have a formula that could help us calculate how long it would take to do something, or how many deer we'd have at a certain period of time, right? How many we're going to have based on that doubling time, or that half-life. And this is what we're going to get into next, our calculations with doubling time and half-life. So our calculation for doubling time, to find a new value, we can take the initial value and multiply by 2 to the power of t divided by t double. This little t represents the amount of time that has passed. The t double is representing the doubling time. And then the second formula, the calculations with half-life, the new value is equal to the initial value times 0.5 to the power of t divided by t half. T half is representing the half-life. So we have two new formulas here, and I think they make sense, right? How did we do this previous example with the deer? The new value, well, it started with the initial value, 30, and then we had one doubling period. We had 20 years, and so that's one doubling period. We got 20 times 2, 30 times 2 to get to 60 deer, and then we had two doubling periods. 60 times 2 gave us the 120. So it makes sense, we're just doubling the time divided by that t doubling, right? If we're halving, we're multiplying by 1/2 of the population, or 1/2 is the same as 0.5. So we're taking 0.5 times the population. Let's take a few examples. Example 4, a city's population grows at a rate of 4% per year. The population in 2010 was 25,000 people. Find the population in 2050. So the first thing I need to find is the doubling time. I'm going to do this the same way we did before. We're going to take 70 and divide it by the 4. And we get 17.5 per year. Tells me this would be 17.5 years. I want to know how many people there will be, the new value, in 2050. So I'm going to be looking for this part of my equation. I have the t double, but I don't have little t yet. Little t is the time that's passed. So little t is going to have to be equal to 2050 is when we want to know, minus the 2010 is where our first population number was given. That's 40 years. So now we have enough information to do this calculation. The new value will be equal to the initial value of 25,000 times 2 to the power of 40 divided by 17.5. I type this into my calculator. Now around this exponent, I didn't put it there, but it's very important that we use parentheses. If we don't use parentheses in our calculator, depending on our calculator, some calculators kind of do this automatically, but if our calculator doesn't, it's going to give us the wrong answer. So it is important to make sure we're using those parentheses. And so what we'll see, we get a value of 121,901.37. I'm going to just round that to the nearest whole. That'd be 121,901 people. Let's think about if that makes sense. We knew the population would double every 17.5 years. That means in 40 years it will have doubled twice. We started with 25,000 people, double that, that's 50,000, double it again, it's 100,000. So we knew it was going to be over 100,000 because it has to double every 17.5 years, so it's doubled twice. Didn't double 3 times, so we wouldn't have expected 200,000. So this answer seems very, very reasonable. The nice thing about that doubling time is it gives us something that has to work within reason. Let's look at another example. A certain drug leaves the bloodstream, apologies on that typo, leaves the bloodstream at a rate of 8% per hour. If a patient takes 20 milligrams of the drug initially, how much will be remaining after 6 hours? So let's start by calculating that T double or T half. Here we have the drug leaving the bloodstream. That means we're dealing with a decrease, T half. Going to take our 70, we're going to divide it by 8, and 70 divided by 8 gives us the half-life of 8.75. This would be hours. So the drug will become half of what it was every 8.75 hours. RT is 6, and that was just given to us directly. 6 hours have passed. So our new value is going to be equal to the initial value of 20 milligrams, times, this time I have to use 0.5 or 1/2, and you can use 1/2 instead of 0.5. 0.5 probably just a little bit easier to type into the calculator. Our time is 6 divided by our half-life of 8.75. So I'm going to type this in the calculator. Again, be careful with parentheses. We want to make sure we include those. I have 20 times 0.5 to the power of 6 divided by 8.75. And we get an answer of 12.43. I'm going to round it to decimal places. So there would be my second answer. Let me clean that 3 up a little bit. That is a 3. So here we can see that we didn't quite end up with half of what we started with. We started with 20 and we didn't get down to 10, and that should make sense. We found the half-life was 8.75 hours. We've only gone 6 hours, so we haven't reached the amount of time it would become half. So a little bit over that though, 12.43 is very reasonable. Let's take a look at this last example. Polluted river is found to have 50,000 tons of trash in it. The city has undergone a cleanup program for the last 20 years where they got rid of 16% of the trash in the river every year. How much trash was in the river 20 years ago? So if we come back up to these formulas, we are dealing with a half-life again. We're getting rid of trash, it's going away. And this time we actually are given the final value, 50,000 is what they have now. We want to know the initial value. So we're going to have to solve this one a little bit differently. Let me start by finding the half-life. So T half, we're going to take our 70, we're going to divide it by the percentage. This is always the easy calculation. And when we do this, we get the 4.375 is 16% of the trash every year. So this would be 4.375 years is our half-life. Next, we're going to set up the equation to solve for how much we started with. Well, we now have 50,000 tons. We don't know the original value, just call it original. I'm going to multiply this by 0.5 to the power of the total time elapsed is 20 years divided by 4.375. And so we have two options at this point. We can go ahead and calculate this number. I'll just say it out loud. I'm not going to write it down yet. That number is approximately 0.042059. And we can, once we get that number, 0.04, we have our unknown here. We would need to divide that number over to the other side to get the original number by itself. We could also just go ahead and divide at this point. It makes no difference. But again, we are dividing in order to be able to get the original value by itself. Now, if we're going to type this into the calculator, just like with before, we want to make sure we're putting that exponent in parentheses. And so let me go ahead and do this calculation in my calculator. And we get the answer, 1188795.43. I'm going to round to the nearest whole. So that would be 1,188,795 tons of trash. So the city has done quite well for themselves. They've gotten rid of a lot of their trash. If we look at the half-life, 4.375 years, every 4.375 years they have halved the amount of trash. So they've gone through almost 5 full iterations of that, 20 divided by 4-ish, almost 5. They've halved the amount of trash 4 times over, almost 5. And so we can see that we've gone from a very, very large number, 1 million tons of trash, down to just 50. And that is the power of this exponential growth. You can make numbers really, really large or really, really small in a fair, quick amount of time. Again, all the calculations we've done today are approximations. We have done this with the rule of 70, which that step there does approximate. So there are ways to get these values as exact values, but the rule of 70 gives us a really, really quick way to approximate exponential growth and decay.